Okay, last class we have seen impedance of the transmission line with respect to y. With respect to y, what is y? Y is the distance measured from the load to source. Y is distance measured from load to source. Okay, so that impedance with respect to impedance of the line with respect to y is equal to zy. Okay, zy is equal to z naught zl plus z naught tan h gamma y uh, divided by z naught plus zl tan h gamma y. Okay, now for a lossless line, okay, for a lossless line, gamma is equal to j beta. Okay, for a lossless line, gamma is equal to j beta. Then you replace gamma with respect to j beta. Then zy is equal to z naught zl plus j z naught tan beta y divided by z naught plus j zl tan beta y. If y is equal to L, say for example, this is your transmission line, this is y is equal to 0, then once if you move in this direction, then this is y is equal to L. If y is equal to L, you are exactly at the source end, then your impedance is called as input impedance. So your impedance is called as input impedance. So if y is equal to L, okay, zy is equal to z naught zy is equal to z in input impedance of the line, then z in is equal to z naught zl plus j z naught tan beta l divided by z naught plus j zl tan beta l. Okay, now for a lossless line, okay, if the line is lossless, then definitely again for a lossless line, this is the input impedance, because already you have applied the lossless condition. Now you have replaced y with respect to L. Okay, for a lossless line, okay, at y is equal to L, this is the input impedance. Now this is the input impedance values. Input impedance z in is equal to z naught zl plus j z naught tan beta L divided by zl plus j zl tan beta L. Now we can also write this equation in terms of normalized impedance format, because if you have any impedance, that impedance can be normalized. Suppose if you have impedance Z, once if you divide by Z naught, characteristic impedance of the line, then that is called normalized impedance. That is called normalized impedance. Okay, normalized impedance. Okay, but if you have z naught, if you are normalizing z naught with z naught, then definitely z naught divided by z naught. So the normalized impedance of the characteristic impedance is always 1. Okay, always 1. So once if you apply that condition, once if you normalize all the impedance given there, just you divide all the impedance with respect to z naught, then the first one is z in bar, the z naught by z naught is 1. Okay, then zl bar, okay, zl bar plus j uh, tan beta l divided by 1 plus 1 plus j zl bar tan beta l. Okay, tan beta l, this is the input impedance in the normalized format. Input impedance in the normalized format. Now what happens when you have open circuit or short circuit line? Okay, so now you analyze the properties of open circuit and short circuit line. Okay, say this is your I take this as the final equation. It's always better to remember this equation. Okay, to remember this equation, then from this we'll proceed. Okay, from this we'll proceed. Okay, um, now once if you have that equation, then when one by one I'll proceed. Case 1. Okay, the case 1 is if ZL is equal to Z naught, what happens? If ZL is equal to Z naught, then we'll see under both the condition, under lossy as well as lossless, what happens. Okay, then I should know both the formula, lossless and lossy formula. For lossless, okay, say this is for lossless. Okay, ZY is equal to Z naught, ZL plus Z naught tan H gamma Y, then Z naught plus ZL tan H gamma Y. This is the condition for lossy line. Okay, line with loss. Okay, okay, lossy line. Condition for lossy line. Okay, then here if you substitute, if ZL is equal to Z naught, if ZL is equal to Z naught, then ZY is equal to Z naught plus uh, okay, ZL is equal to Z naught, then ZY is equal to Z naught. So Z naught plus Z naught tan H gamma Y, then Z naught plus Z naught tan H gamma Y. Okay, so both the numerator and denominator is same. Finally, you are getting Z naught. So okay, so once if you terminate your load impedance with the load with the impedance, with the characteristic impedance, okay, load impedance with the characteristic impedance, then your impedance is always Z naught. Even if you measure at the input side, definitely instead of Y you'll get L, then they are also cancelling with each other. So finally your input impedance is Z naught. Input impedance is Z naught. Now if it is lossless, okay, if the line is of with no loss, okay, then you will have some other formula. Okay, if line is of lossless, okay, for lossless, okay, for lossless you will have this formula: Z in is equal to Z naught, okay, okay, Z naught, okay, ZL plus J Z naught tan beta Y, and Z naught plus J ZL tan beta Y. Okay, once if you substitute ZL is equal to Z naught here, then your Z in is equal to again Z naught plus J Z naught tan beta Y, and divided by Z naught, okay, Z naught plus J Z naught tan beta Y. Again, both the numerator and denominator is same. This is equal to Z naught, then Z in is equal to Z naught. Okay, Z in. Then instead of Z in, you can put ZY here, because here it is Y, here it is Y. But even if you calculate Z in, ZY is Z naught, then Y can be anything. So if you substitute Y is equal to L, then also your input impedance is equal to characteristic impedance. So the conclusion is, once if you have a line that is terminated with Z naught, irrespective of the nature of the line, let it be lossy or lossless, then always the impedance seen at any point on the transmission line is always Z naught, any point on the transmission line. So what is the meaning of this one? See, if you have first case, say for example, if you have lossy line, the next case you are having lossless line. Okay, lossless line. What we are doing, we are terminating the load. Okay, ZL we are taking is equal to Z naught. Once if you take in this manner, if you terminate ZL with Z naught, similarly here also instead of ZL, if you are taking Z naught, okay, whatever may be the nature of the line, and wherever you measure the impedance, say you can measure here, always that is Z naught, always that is Z naught. Okay, you measure anywhere on the transmission line, your impedance remains same irrespective of the nature of the line. Okay, irrespective of the nature of the line. So whenever you have a line, transmission line, if it terminates at ZL is equal to Z naught characteristic impedance, then the impedance seen anywhere on the transmission line or at the input of the transmission line is always Z naught, is always Z naught. So what is the conclusion? The conclusion is, okay, if ZL, if in transmission line, if load is terminated, if load is terminated with Z naught, then irrespective of nature of the line, irrespective of nature of the line, that means what? That is either lossy or lossless. Irrespective of nature of the line, let it be either lossy or lossless, irrespective of the nature of the line, the impedance measured anywhere on the line or at the input, impedance measured anywhere on the line or at input is always Z naught. That simply I can write Zn is equal to Zy is always is equal to Z naught, is always is equal to Z naught. So an important conclusion. Similarly, what happens once if you have the short circuit line, what happens? We'll see. Okay, if you have short circuit line, okay, short circuit line or impedance or load impedance is 0 ohm. Once if you have short circuit line, then what happens to the um what happens to the uh, input impedance of the line? Okay, input impedance of the line. Now the input impedance, when for lossless, okay, for first we'll write for lossy condition, the input impedance is equal to Z naught plus ZL plus Z naught tan H gamma L divided by Z naught ZL tan H gamma L. Okay, now you substitute ZL is equal to 0. Once if ZL is 0, 0 plus Z naught tan H gamma L. Okay, then 0, uh, not 0, Z naught plus 0, Z naught plus 0. Then Z naught cancels. Finally, you'll get Z naught tan H gamma L. So your input impedance is equal to Z naught tan H gamma L. Similarly, for lossless, once if you have lossless line, then input impedance of lossless line is equal to uh, okay, this one, with the help of with the instead of gamma, you'll get beta. Okay, so J ZL tan beta L. Then you substitute values Z naught 0 plus J Z naught tan beta L divided by Z naught plus 0. Then Z naught cancel. Finally, you are getting J Z naught tan beta L. Okay, this is the input impedance of the short circuit line. Whenever you have a short circuit line, this is the input impedance. Zin is equal to J Z naught tan beta L. Similarly, we will derive it for open circuit. Okay, open circuit line, or ZL is equal to infinite. ZL is equal to infinite. And here also, what is the condition for a lossy line? Once if the line is lossy, then Zin is equal to Z naught ZL plus Z naught tan H gamma L divided by Z naught ZL tan H gamma L. Then you substitute the value of ZL is equal to infinite. Once if you substitute infinite divided by infinite is not in a proper format, then you take ZL outside, you just modify the equation. Once if you modify, it goes like this, 1 plus Z naught divided by ZL tan h gamma l divided by z naught, okay, z naught divided by zl, then plus, okay, z naught divided by zl, okay, you are taking zl outside from both. So once if you take outside, then it comes like this: z naught divided by zl, then this is tan h gamma l. Okay, once if this is like this, then you substitute zl is equal to infinite, then what happens? Z naught 1 plus 0, then 0 plus tan 0 plus tan h gamma l, 0 plus tan h gamma l. What happens once if tan h goes up? Then that is z0 cot h gamma l. Similarly, for lossless line, the input impedance is equal to z0 zl j z0 tan beta l, okay, and z0 zl tan beta l, and again once if we directly substitute infinite by infinite, that is not in proper format, you take z0 from both numerator and denominator outside, then 1 plus j z0 divided by zl tan beta l divided by z0 divided by zl plus tan beta l. Okay, again j will be there here. Here also j will be there. Then you substitute zl is equal to infinite, then z0 1 plus 0 divided by 0 plus j tan beta l. Now if the tan beta l goes upwards, then again j is there, minus j cot beta l. So finally minus j z0 cot beta l. Okay, this is the uh, input impedance for lossless line when if the load is terminated at a open circuit. Load is terminated with the open circuit. Now I can put a table by comparing all these things. See, when zl can be z0, zl can be z0 or 0 ohm or short circuit or infinite ohm or open circuit. Now what happens if the line is of lossy or lossless? Okay, lossless. Uh, once and again this is the input impedance. Okay, this is the input impedance. Now I put the table. Okay, I put the table. I put the table like this. Okay, so and again this is z0, this is also z0, this is z0 tan h gamma l, this is j z0 tan beta l, this is z0 cot h gamma l, this is minus j z0 cot beta l. Okay, so exam point of view, this section is very important because in the exam mostly they'll ask for lossless condition. So please always try to remember for lossless conditions. Okay, lossless condition. And how to remember very easily? Once if you have short circuit, or once if it is of open circuit nature, say is at OC, then you simply think of OC, or you would just reverse it, then you'll get CO. CO means what? Cot. Okay, cot beta L. Okay, whenever cot comes, then you just put minus J Z naught. Or otherwise, what is the other format, opposite format? Okay, instead of cot you will get tan beta l, instead of minus j z naught you will get plus j z naught. So simply you can remember, and this one is very easy. Okay, this is always z naught only. Once if load is terminated with z naught, then input impedance is always z naught only. So this is some simple way to remember, okay, this formulas. Next we will see the properties of lambda by 2 and lambda by 4 and lambda by 8 line, the two for lossless case. Okay, the two for lossless case. Okay, so properties of lambda by 2, lambda by 4, lambda by 8 line under lossless condition. Okay, under lossless condition. First I take the lambda by 2 line. Okay, lambda by 2 line, that means what, length of the line is equal to lambda by 2, because you are operating in some frequency. Once if you operate at some frequency, you can calculate lambda. Lambda is gives you the wavelength, but once if you know the wavelength, then you just divide it by 2, then you will get some length. Then you take the transmission line length, that is equal to lambda by 2. Okay, that is the lambda by 2 line. Okay, once if you have lambda by 2 line, okay, say for example this is your line. Okay, this is your line lambda by 2 line, then you connect some load here, you connect some load ZL. Once if you connect some load here, then the length of the line is lambda by 2, then we are going to identify what is the input impedance. Okay, once if you have lambda by 2 line, then the load is terminated with the ZL, then what happens to Zin, input impedance. Now see, and we are under lossless condition. So once if you are under lossless condition, then Zn is equal to Z naught ZL plus J Z naught tan beta L divided by Z naught plus J ZL tan beta L. Okay. Now again beta L is there. You know what is L, length of the line. Then you just compute beta L. Okay, beta L is equal to 2 pi by lambda, and lambda by 2, lambda cancels, 2 cancel, then beta L is equal to pi. Now you just substitute in the equation pi value, Z naught ZL plus J Z naught tan pi, and then Z naught J ZL tan pi. You know the value of tan pi is always 0, then you get this one alone. Okay, ZL plus 0 divided by Z naught plus 0, then Z naught cancel. Finally you are getting Zin is equal to ZL, Zin is equal to ZL. That means what, when you have lambda by 2 transmission line, if you terminate the load with ZL, then your input impedance is same as the load impedance. Your input impedance is same as load impedance. So or this can also be extended, because even if you have another lambda by 2 section, again you will get the same impedance, because for every lambda by 2, whatever the characteristic that you are having, that is getting repeated. That's why in general I can write like this: impedance of lambda by 2 or n lambda by 2 line is always same as load impedance. Line is always same as load impedance. Always same as load impedance. Okay, what is the meaning of this one? Okay, say for example, if the line, say if the line is lambda by 2, if somebody gives this is ZL, then they ask what is the input impedance here, then definitely that is ZL only. Similarly, if some line is here like this, and it is terminated with ZL, and the line length is say 51 lambda by 2, line length is 51 lambda by 2, then they ask what is the input impedance, then also the input impedance is same input impedance only, ZL. Or if somebody comes and gives the length of the line is say 100 lambda by 2, okay, length of the line, and they terminate the load ZL, then what is the input impedance? Now also the input impedance is again same only. So that is the idea of this lambda by 2 line. Okay, once if you have lambda by 2 line, then impedance remains same. Okay, next we'll have lambda by 4 line. Okay, lambda by 4 line. The another name for lambda by 4 line is quarter wave transformer line. Quarter wave transformer line. Quarter wave transformer line. Now, once if the length of the line is lambda by 4, say this is lambda by 4, you are connecting with some load impedance ZL. Now what happens at the input side? Now we have to analyze this one. What happens? Once if you know L length of the line, then first of all you have to calculate what is beta L. Beta is equal to 2 pi by lambda, and L is equal to lambda by 4. Then that is simply pi by 2. Okay, then you apply in the equation. The base equation is Zn is equal to Z naught ZL J Z naught tan beta L divided by Z naught plus J ZL tan beta L. Okay, now tan pi by 2 divided by tan pi by 2, infinite by infinite, that is not in a proper format. Then you just modify this equation. Okay, you divide both the numerator and denominator with respect to tan beta L. Once if you do that, okay, it comes ZL divided by tan beta L J Z naught divided by Z naught divided by tan beta L plus J ZL. Okay, once if it is like this, then tan beta L is tan pi by 2. Tan pi by 2 means what? Infinite. Once if you substitute, then this will become 0. Then J Z naught 0 plus J ZL. Okay, J cancels, then Z naught square divided by ZL. So what finally you are getting? Finally your input impedance is equal to Z naught square divided by ZL. Z naught square divided by ZL. Okay, so this particular line is called quarter wave transformer or impedance transformer, because see what is happening once if you have the formula like this. Okay, so your input impedance is equal to Z naught square divided by ZL. Z naught square divided by ZL. What is the meaning of this one? Say if you have a line like this, lambda by 4 line, if you connect some high impedance here, load impedance, high value, then what you will observe here? You will observe low impedance, because as per this formula, Z naught is constant for a given line. Once if ZL increases, Zn will decrease, or otherwise, if this is low, then this will be what? High. This will be what? High. Okay, because if ZL is low, then Zn will be high. That means what? It transforms the impedance from high to low or low to high. Low to high. That's why this section of the transmission line is called as quarter wave transformer or impedance transformer, because it transforms the impedance, okay, high to low or from low to high. Okay, this quarter wave transformer is called as impedance transformer, impedance transformer, because it transforms high to low or low to high, transforms impedance from high to low or from low to high. Okay, so and again in general, how can we write this one? So once if you have lambda by 4, suppose if they introduce n lambda by 4, now the n can be even or n can be odd. If n is even, definitely finally you will get n lambda by 2 format, because if n is even, almost you will get something similar to n lambda by 2 or similar to lambda by 2 line. But once if lambda by 2 line is that, then nature goes to similar to the lambda by 2 line. But if n is odd, okay, if n is odd, then you can write this one with like this, lambda by 2 divided by lambda by 4. Now you know that whenever you have lambda by 2 line, there will not be any change, there will not be any change, but only there will be the effect of lambda by 4, effect of lambda by 4. That's why the n lambda by 4 line is similar to, will behave similar to lambda by 4 line when n is odd, when n is odd. Okay, so when n is odd, n lambda by 4 line is similar to lambda by 4 line, lambda by 4 line. Okay, so say for example in the exam, if they give like this is the length of the line, this is ZL, then if somebody asks what is the input impedance here, input impedance is Z0 square divided by ZL. Or otherwise they give 10 lambda by 4 like that, then what is the meaning of this one? Once if you connect ZL, no need to follow this formula because 10 is even number. Once if it is even number, it will behave similar to lambda by 2 line, then this is simply ZL only. This is simply ZL only. Or if they give like this, something like this, 31 lambda by 4 ZL, then it will behave similar to lambda by 4 because this number is odd number. Then also your Zn is equal to Z0 square divided by ZL. Okay, now once if you have a lambda by 4 transmission line, for lambda by 4 line, your input impedance is Z0 square divided by ZL, or otherwise your Z0 square is equal to input impedance ZL, then Z0 is equal to Zn into ZL square root. Okay, the characteristic impedance of the lambda by transmission line is the geometric mean of input impedance as well as the load impedance. Okay, for a lambda by 4 transmission line, okay, characteristic impedance is geometric mean of input impedance. Impedance is geometric mean of input impedance and load impedance, input impedance and load impedance. Okay, so input impedance and load impedance. Next we'll see what is the nature of the lambda by 8 line, lambda by 8 line. Okay, lambda by 8 line. Okay, once if it is lambda by 8, then beta is equal to 2 pi by lambda. Then what is L? L is equal to lambda by 8, then pi by 4 is coming. So the length of the line given is lambda by 8. Okay, you are connecting some load here, ZL, then you want to measure what is the input impedance. Okay, then what is our formula? Our formula is Zin is equal to Z0 ZL J Z0 tan beta L divided by Z0 J ZL tan beta L. Okay, then once if you substitute, okay, Z0 is equal to ZL plus J tan pi by 4, that is simply J Z0 plus J ZL. Okay, what you can do, just okay, you can take modulus. Once if you take modulus on both sides, it comes like this. Now after taking the modulus, the numerator and denominator is looking same, then finally you can write like this: Zn is equal to mod Z0, Zn is equal to mod Z0. From this, the input impedance of a line is same as the, okay, the magnitude of input impedance of the line is same as the magnitude of Z0. Okay, what is the conclusion? The magnitude of, from this, magnitude of input impedance of lambda by 8 line is same as magnitude of characteristic impedance. magnitude of characteristic impedance. Okay, one thing you have to note down here. See, finally we are getting Z naught. Finally, you are getting mod Z in is equal to Z naught. Okay, but in general, Z naught is of real nature. Generally, it will not be complex for a lossless line. In general, okay, mod Z in is equal to, you can write Z naught itself, because Z naught is going to be a real quantity. So you cannot, no need to put modulus. Okay, Z naught. But what is the meaning of this one? Your input impedance is not equal to Z naught, but your magnitude of input impedance is equal to Z naught. Once if you know the magnitude, say if you know the magnitude, is it possible to calculate the original impedance? It's not possible. Once if we know the magnitude of something, do not know what is the original, because that is irreversible. That can be anything. But if you know input impedance, you can calculate magnitude. But we are not having this condition, but we are having this condition. That means what we know, we do not know exactly what is input impedance. Only thing we know, the magnitude of input impedance is same as the Z naught. See, I will get some input impedance. I will get some input impedance like this, R plus J omega L. No need to write R plus J omega L. Some real part or imaginary part. Okay, I will get some input impedance that consists of real part, real plus imaginary. That can be anything, that I don't know. Okay, that could be anything. But what is known to me, but once if you take magnitude of this one, once if you take the magnitude of this one, the real part square and imaginary part square root, then that should be equal to, Z naught. That is the idea here. That is the idea. We do not know exactly what is the input impedance, but we know what is the magnitude of the input impedance. What is the magnitude of the input impedance? Again, that particular input impedance nature may be capacitive or inductive, but we do not know. Okay, so we know only the magnitude of the input impedance, magnitude of the input impedance. Okay, with this I will stop. Or otherwise I will compare all these things. Okay, when you have lambda by 4 lambda by 2 line. Okay, once if you have lambda by 2 line, then your input impedance is similar to load impedance. Okay, or otherwise lambda, you can have lambda by 2 or any n lambda by 2. Once if you have lambda by 4 or n lambda by 4, then your input impedance is equal to Z naught square divided by ZL, but n has to be odd. N has to be odd, but n is odd, because if n is even, then that will go to first condition. If n even here, if in this case if n even, then it automatically goes to this condition. Next, we had lambda by 8 line. Okay, we had lambda by 8 line. Then once if it is lambda by 8 line, then your input impedance magnitude is similar to characteristic impedance magnitude, but this also you can write very simply without any magnitude. Okay, this is the comparison of lambda by 2, lambda by 4, and lambda by 8 line. Okay, so we'll stop with this.